Okay, so we'll continue with our study of the Reynolds transport theorem. What we saw in the previous segment was a basic introduction to the Reynolds transport theorem. We showed the main result from it, and we also made a connection to how it can be applied to understand the evolution of mass for the case of a deforming body, right? And in particular, we saw that what it tells us is that, well, the mass does not evolve, the mass is fixed. And in fact, it ties in very nicely with a result that we derived in a previous segment, okay, which also tells us that the mass is fixed in a certain sense because of the fact that the reference density is fixed, okay? All right, so we'll continue now. So the Reynolds transport theorem. Okay, continued. All right. So let's just write down our basic result, which is the following, right? It is that if we want to compute the derivative with respect to time of a quantity, which is an integral over the current configuration of some spatial field okay, where the elemental volume is a volume element in the current configuration, therefore written as d little v. And we saw that this is actually quite easy to do after some calculus, right? Some integral calculus. What we discovered is that this is in fact just the partial time derivative of psi plus the divergence of psi multiplied by the velocity, right, the spatial velocity of the deforming body, right? All of this integrated over d little v. Okay, so that's our general result. And then we saw, of course, how this can be applied to the mass density in the current configuration, and how that leads to a result that makes sense. Okay, so what we're going to do now is sort of prepare ourselves for other such applications of the Reynolds transport theorem. And in particular, we want to think of situations where this quantity that we have, the quantity of interest, is best expressed as something per unit mass. Okay? So, suppose we have psi, okay, defined per unit mass. Okay, then the quantity we want to consider is the following. Okay, if we have this, then the integrals of interest right, the integrals of interest are of the form I of t equals integral over omega t. Now, psi not by itself, but psi multiplied by the mass density in the current configuration integrated over d little v. Okay? The reason this works is that now we are thinking of psi as being defined as per unit mass. Okay? And in multiplying it by the spatial mass density, right, by the current mass density, what we're doing is convert that integrand. Once again, we have an integrand that's defined per unit current volume. Okay, and then that integral makes sense. Okay? What we will see is that it is quite common to have these kinds of objects showing up. We will see in particular that it will be natural at various times in our development that comes to do things like psi, we will see, could be an energy per unit mass. Okay? Okay, this is an example, okay? How could psi be an energy per unit mass? Well, we have the velocity, right? We could take the velocity and just construct this quantity, right? Just the Euclidean norm square of the velocity, okay? Maybe 1/2 of this. And this is in fact the kinetic energy per unit mass. Okay? Right, so this is the kinetic energy okay? And in fact, if you just look at V itself, right? V can in fact itself be thought of as simply the momentum per unit mass. Okay, the velocity itself is simply the momentum per unit mass, right? This is just the okay. So these kinds of objects will be, when they need to be treated, we will need to go to the sort of integral that I've written up here. Okay, when we need to consider questions of energy and momentum, we will often use the Reynolds transport theorem in the form that I've just circled, where psi would be either the kinetic energy per unit mass or even just the momentum per unit mass. Okay, so it's for this reason that we need to figure out what happens with this integral that I've just written here. Okay, so how do we treat it now? So now the question we are asking is, what we need to do is calculate d dt of the following quantity. And what I'm going to do is actually rewrite the same thing, but now making the arguments clear here. So we have rho being the mass density per unit current volume. It's rho parameterized by little x and t. And we have psi also a spatial field. So we have that. Okay, so this is what we want to compute. But if you look at that, you observe that actually there is nothing to do here because we already know the result. Simply observe that this product itself is some other field, right? Let's call it chi x comma t, right? So we can just apply our result from Reynolds transport theorem, okay? As a result, what this tells us is that this quantity we want to calculate is just integral over omega t, okay, of the following. The proper partial time derivative of rho psi, okay, and I'm suppressing arguments because otherwise this will get just too big to write. Right, that partial time derivative plus the divergence of rho psi v. Okay, right? This just comes from the Reynolds transport theorem. I'm going to abbreviate Reynolds transport theorem to RTT. Okay, R for Reynolds, T for transport, and T for theorem. Okay, So we have this result, and we're not done. We can do a little more with it here. Okay, so what I'm going to do now is to just rewrite this in a slightly different form. We know yet another way to write it is this, right? We could always write it as, what we could do is just rewrite this as follows, right? I'm going to break up the first term, that first partial time derivative, using the product rule. Okay, so we're going to write it as rho partial time derivative of psi plus psi partial time derivative of rho. Okay, that second term I'm going to combine by writing, we have a product in the second term involving rho, psi, and v. Okay, I'm going to group that so that rho and v are together and psi is sort of treated as a separate function. Okay, so what this means is that now I'm going to write that again by applying the product rule, right, of differentiation of any type of derivative, right, including the divergence, right. The way I can write that is as follows. I can write that as psi times divergence of rho v, okay, plus rho v dotted with gradient of psi. Okay, all of this. Okay. Now, I think the first two terms should be fairly clear. Just to show what happens with the third and fourth terms, how those come about, I am going to go into coordinate notation. Okay, so okay, so what we're considering here is this term, divergence of rho psi v. Okay, rho and psi are scalars, v is a vector, so this is just derivative with respect to x sub I of rho psi vi. Now, the way we decided to combine this was to take rho and v together and psi by itself. Okay, so when we do this, we get psi derivative with respect to xi of rho vi plus rho vi derivative of psi with respect to xi. Okay, and here we have it, because now we observe that this is just divergence of rho v. Okay, whereas this term is just rho v dotted with that term which is gradient of v. Okay, and what I have here, that term is that one, and that term is that one. Okay? All right. I'm going to go to the next slide, and I am going to gather terms there. So what we have then is that d dt of I comma t, I is a function of t, is integral over omega t. Okay, I'm going to group the terms where psi was not involved in a derivative, right? So that those terms were psi partial time derivative of rho with respect to time plus divergence of rho v. Okay, and the next term was rho times partial time derivative of psi plus V dotted with gradient psi. Okay? This is what we had on the previous slide. I've just grouped terms differently. But now I ask you, what is this? What I've just drawn a brace under is in fact what we obtained as the left-hand side of our mass conservation equation. Okay? This term therefore is dead zero from conservation of mass. All right? And so we see that when we have this quantity psi that's defined per unit mass, then when we consider the time rate of this integral I, which we defined on the previous slide, right? What this implies is that d dt of I function of time, which is d dt of integral over omega t of rho psi d little v. When we have an integral of this type, and when we're trying to compute its time derivative, what we're left with is integral over omega t rho derivative, the partial time derivative of psi plus the convective term. Okay? But then we observe that this is just the partial time derivative of psi parameterized by x and t, where we remember that x is obtained through the motion, right? And here we are keeping this reference position fixed. Okay? So we have this nice, this is what this integral reduces to. It can be further elucidated and sort of simplified when we observe that the product rho with d little v gives us a mass element. Okay? So equivalently, we can think of this as an integral over the volume, okay, over the spatial volume, right, over the spatial configuration of this material time derivative of psi, where we are remembering that psi is parameterized by spatial position in time, but then we are remembering that the type of time derivative we are taking is a material time derivative. Okay? This times d little m, where d little m is a mass element. Okay? So dm is a mass element. Okay? So this gives us a nice simplification of this case of these sorts of cases where psi is properly defined as a quantity per unit mass. So essentially this thing is telling us is that if psi were something like your energy per unit mass, this is how you would compute the time rate of the total energy. Okay? You would be computing this material time derivative of the energy per unit mass and simply effectively integrating it over mass elements. Okay? Likewise with the volume. If psi were something like a volume, sorry, not a volume. If psi were something like a momentum, you would be doing this sort of integral where now instead of where psi would represent a momentum per unit mass, and we looked at the example where momentum per unit mass is in fact the velocity. All right? Okay, we're going to stop this segment here.